Ladies and gentlemen, something happened on a 3,000-mile journey that was never supposed to happen in a machine designed to think, predict, and correct itself before failure even exists. A silent system alert triggered inside a moving intelligence network, not because of a breakdown but because of something far more unusual, something the machine detected before any human awareness could even react. Across highways, satellites, factories, and invisible AI systems operating at global scale, every connected layer instantly shifted its behavior, as if the entire world of machines had paused for a deeper inspection. This was not just a vehicle on a road anymore. It was a living data stream feeding millions of calculations per second into robotic factories, predictive simulations, and autonomous systems that began rewriting their own understanding of reliability in real time. And what they discovered hidden inside that signal changes everything you think you know about modern technology, automation, and the machines already shaping the future in silence. And the move was supposed to be simple. A fully loaded vehicle. Over 3,000 miles of highways, automated logistics routes, charging corridors, weather prediction systems, and AI-assisted navigation, all synchronized into one seamless journey. Every mile calculated, every stop optimized, every system communicating in real time like a rolling data center on wheels. But somewhere between state lines, desert heat, and endless stretches of asphalt, something unexpected appeared. A leak, and not just a random drip. Not a simple mechanical issue from the past. This was different. The kind of discovery that instantly changes the entire perception of modern transportation systems. Because when advanced machines are designed to operate with near-perfect efficiency, even the smallest anomaly becomes a signal. A warning hidden inside layers of technology. And at first everything looked normal. Battery temperatures remained stable. Autonomous driving sensors continued scanning traffic with millisecond precision. Suspension systems adjusted dynamically as road surfaces changed beneath the tires. Energy consumption models recalculated every second, based on terrain, wind resistance, elevation, and driving behavior. The machine was functioning like a moving supercomputer. And then came the alert. And a subtle notification buried inside the diagnostics interface. Tiny fluctuations in pressure readings. Microscopic inconsistencies detected by onboard monitoring systems, designed to observe thousands of variables simultaneously. Systems most drivers never even realize exist. Advanced leak detection algorithms comparing real-time data against millions of historical patterns stored across cloud-connected infrastructure. And then suddenly the impossible question emerged. And how did a leak appear inside one of the most advanced transportation platforms ever built? And what makes this story so fascinating is not just the leak itself. It is what happened next. Because modern vehicles are no longer simple machines. They are intelligent ecosystems. Rolling networks of sensors, processors, cameras, thermal management systems, predictive software, and automated diagnostics operating together at extraordinary scale. And the moment the issue appeared, the vehicle began responding before human intervention even became necessary. And internal systems isolated irregularities. Thermal balancing modules adjusted automatically. Pressure routing systems recalibrated in real time. AI-driven predictive maintenance protocols analyzed potential outcomes faster than any traditional mechanic ever could. The vehicle was essentially diagnosing itself while traveling across thousands of miles at highway speed. And this is where the future becomes almost unbelievable. And the leak was not catastrophic. It was small, almost invisible. But advanced machines are built differently now. Tiny inefficiencies matter because modern technology operates at precision levels older systems could never achieve. A single seal under extreme environmental conditions. Continuous high-speed operation. Weight load shifting across long-distance travel. Heat cycles repeating for days. Every variable compounds. And what older generations would have ignored, next-generation systems detected instantly. And imagine driving through massive desert corridors where temperatures climb beyond expectations. The road stretches endlessly ahead while automated navigation systems continuously optimize power distribution between motors and battery architecture. Cooling systems operate with surgical precision, circulating fluids through networks engineered for maximum efficiency. Everything is balanced perfectly until one microscopic weakness disrupts the equation. And that is the reality of high-tech mobility. And the fascinating part is how machines now communicate these problems. Not through smoke, not through loud mechanical failure, through data, through patterns, through invisible digital intelligence observing changes humans cannot physically see. Vehicles today are constantly predicting future outcomes, estimating where, calculating probabilities, monitoring performance like aerospace systems, and during this 3,000-mile move the technology revealed something shocking. The future of transportation is not about eliminating problems entirely. It is about detecting them before they become disasters. And as the miles continued, cloud-connected systems, synchronized diagnostics remotely, performance logs updated in real time. Charging stations along the route became checkpoints inside a larger automated infrastructure network. Service recommendations adapted dynamically, based on environmental conditions, speed averages, and fluid loss modeling. The vehicle was essentially part of a nationwide intelligent transportation grid. And this is where modern mobility begins feeling less like driving and more like participating in a giant machine ecosystem. And every charging stop generated more data. Cameras scanned exterior conditions automatically. Internal systems ran predictive simulations during downtime. AI compared leak progression rates against massive datasets collected from fleets operating across different climates worldwide. Patterns emerged instantly. Solutions evolved continuously. And yet the mystery remained. And what caused the leak in the first place? And extreme pressure cycles? Long-term thermal stress? Material fatigue at microscopic scale? Unexpected environmental exposure during the move? The answer became secondary compared to the bigger realization. Modern machines are no longer waiting for failure. They are actively hunting for weakness before collapse happens. And that changes everything. And because the future of transportation is not built on perfection alone, it is built on intelligent response systems, automation capable of adapting in motion, vehicles capable of self-monitoring across thousands of miles without interruption, machines learning continuously from every road, every climate zone, every pressure fluctuation, and every hidden anomaly buried deep inside complex systems. And in somewhere during that massive 3,000-mile journey, one tiny leak exposed just how advanced the future has already become. But what made the situation even more extraordinary was the realization that this single vehicle was not operating alone. Hidden behind the dashboard displays and silent electric acceleration was an enormous digital infrastructure stretching across factories, satellites, logistics hubs, robotic assembly lines, and AI training networks distributed around the world. Every sensor reading generated during the journey was feeding into systems far beyond the road itself. And inside advanced manufacturing facilities, robotic production units had already seen millions of variations of component behavior. Automated arms working with sub-millimeter precision assembled cooling systems faster than human reflexes could react. Laser-guided machines scanned structural integrity in real time, while neural network quality systems searched for microscopic imperfections invisible to the naked eye. Entire factories operated like synchronized processors where conveyor systems, autonomous robots, and AI-driven calibration platforms moved in perfect coordination. And then suddenly this leak became part of that giant intelligence network. And the vehicle's onboard systems were not simply detecting a problem. They were contributing data back into a continuously evolving ecosystem of machine learning models. Every temperature fluctuation, pressure imbalance, vibration frequency, and environmental variable became valuable information. Millions of miles driven by connected fleets had created something unprecedented in automotive history, a transportation network capable of learning collectively. And that changes the meaning of machinery entirely. And traditional machines waited for commands. Modern systems anticipate outcomes. And as the vehicle crossed massive highway systems late into the night, onboard processors continued running predictive simulations in the background. AI-driven thermal models calculated how the leak might behave under colder climates ahead. Autonomous efficiency systems adjusted energy routing dynamically to compensate for microscopic losses. Battery conditioning software modified cooling behavior by fractions of a degree, preserving stability without disrupting performance. And all of this was happening silently. And no visible panic. No dramatic breakdown. Just algorithms working continuously beneath the surface, reacting faster than human perception itself. And what makes these systems so fascinating is the scale at which they operate. A single modern electric platform contains thousands of interconnected components communicating simultaneously through high-speed digital architecture. Sensors monitor rotational force, liquid flow, electrical resistance, aerodynamic drag, tire pressure, battery density, cabin climate, external temperature, road texture, and structural stress every second. The amount of real-time data moving through the vehicle rivals complex industrial systems. And when an anomaly appears, the response resembles aerospace engineering more than traditional transportation. And automated diagnostics isolate patterns instantly. AI systems compare live telemetry against historical fleet behavior collected across continents. Manufacturing databases identify whether similar pressure signatures have appeared elsewhere under matching environmental conditions. Robotics engineers receive performance reports generated automatically through cloud-connected infrastructure. Entire production pipelines evolve based on events happening thousands of miles away on open highways. And this is where the story becomes almost surreal. And the leak itself may have originated from something microscopic. A seal exposed to repeated thermal expansion cycles. Material fatigue accelerated by continuous high-speed travel. A tiny structural variance measured in fractions of a millimeter. But modern machines operate at such advanced efficiency levels that even microscopic inconsistencies ripple through enormous digital ecosystems. And factories of the future are designed around this exact philosophy. And gigantic automated facilities now function less like manufacturing plants and more like living computational organisms. Robotic assembly systems move with choreographed synchronization beneath massive networks of cameras and AI-controlled scanners. Parts arrive through autonomous logistics corridors optimized by machine intelligence, predicting supply demands weeks in advance. Every bolt tightened by robotic arms generates measurable data. Every cooling unit tested feeds information into quality learning networks, refining future production. And nothing is disconnected anymore. And the vehicle on that 3,000-mile move was directly linked to production systems still evolving in real time. The moment the leak appeared, software engineers, manufacturing algorithms, predictive maintenance systems, and automated diagnostics platforms effectively gained another case study for future optimization. And this is where artificial intelligence becomes truly transformative. And AI no longer exists only as voice assistants or navigation systems. It now functions as an invisible operational layer surrounding entire industries. It watches production lines continuously. It predicts supply chain slowdowns before they occur. It analyzes fleet-wide component performance across millions of driving hours. It simulates future failures before physical breakdowns happen in reality. And during that long-distance journey, the vehicle itself became part of a machine learning experiment, unfolding live across digital infrastructure at global scale. And even the charging network played a role. And modern charging stations are no longer passive energy points. They are intelligent nodes connected to larger energy distribution ecosystems. As the vehicle stopped to recharge, diagnostic information synchronized automatically through encrypted cloud systems. Charging behavior adapted based on battery temperatures and projected route demands ahead. Power delivery systems balanced electrical loads dynamically across regional grids using predictive demand forecasting powered by AI. And the machine was communicating constantly. And vehicle to charger, charger to network, network to factory systems to engineering simulations, simulations back to software updates, and an endless loop of automation. And perhaps the most fascinating detail of all was how invisible this entire process remained to ordinary observers. From the outside, the vehicle appeared calm, silent, efficient. It continued moving through cities, mountains, deserts, and highways with smooth electric precision. Yet beneath that minimalist surface, billions of calculations were unfolding every hour. And this is the hidden reality of next-generation mobility. And machines are no longer isolated products. They are connected intelligence platforms evolving continuously after production. Every mile improves future algorithms. Every anomaly strengthens predictive systems. Every leak, vibration, or pressure fluctuation becomes fuel for larger machine learning architectures, shaping the next generation of transportation. And somewhere deep inside automated production facilities, robotic systems were already adapting, recalibrating, and preparing for a future where machines do not simply survive problems. They learn from them while still in motion. And inside those gigantic facilities, the response had already begun before the vehicle even completed the journey. Vast production floors illuminated by white industrial lighting stretched across distances that felt almost endless. Autonomous transport platforms moved silently beneath towering robotic structures carrying battery modules, cooling assemblies, and precision-engineered components at astonishing speed. Mechanical arms rotated in synchronized motion like a living machine civilization, operating with mathematical perfection. And every second mattered. And thousands of components flowed through assembly systems without interruption. Robotic welding units released flashes of blue light across metallic frames, while laser scanners inspected structural alignment in real time. AI-controlled vision systems tracked microscopic deviations faster than human eyes could process movement. Massive stamping machines reshaped raw material with explosive force, creating ultra-precise panels engineered down to fractions of a millimeter. And somewhere inside this immense automated ecosystem, the data from that single leak was already moving through neural networks at incredible velocity. And the moment diagnostic information reached centralized systems, advanced simulations activated instantly. Digital twin technology recreated the exact journey virtually. Every highway incline acceleration pattern, ambient temperature shift, charging cycle, and cooling fluctuation was reconstructed inside high-performance computing environments. Entire virtual replicas of the vehicle operated inside simulation chambers, running thousands of alternate scenarios simultaneously. And this was no longer simple troubleshooting. And this was industrial-scale machine intelligence studying itself in real time. And inside AI-driven analytics centers, enormous walls of live telemetry displayed streams of constantly updating information. Pressure graphs fluctuated across digital interfaces. Thermal imaging models visualized microscopic heat variations moving through coolant pathways. Predictive systems accelerated through millions of calculations, searching for correlations invisible to conventional engineering methods. And the leak had become a signal inside a gigantic computational organism. And the scale of response was staggering. And automated quality control systems inside manufacturing plants immediately adjusted inspection thresholds. Robotic scanners increased sensitivity during seal verification procedures. Precision torque systems recalibrated assembly pressure measurements by microscopic margins. AI-driven production software began comparing supplier batch data across thousands of manufactured units. And factories were learning at machine speed. And imagine standing above one of these facilities at full production capacity. Endless rows of robotic arms moving continuously with silent aggression. Conveyor systems transporting structural platforms beneath synchronized assembly stations. Automated drones monitoring inventory movement from above while AI systems optimize traffic flow inside the factory floor like a living nervous system. And nothing stops. And not for day, not for night, not for weather. The entire operation functions with relentless momentum driven by software predicting production flow down to the second. Machines communicate constantly. Sensors exchange information across entire buildings. Autonomous systems reroute materials automatically when inefficiencies appear. Industrial robotics adapt movement patterns dynamically to maximize throughput. And this is not manufacturing from the past. And this is machine civilization operating at planetary scale. And while the vehicle continued traveling across thousands of miles, massive server infrastructures were already calculating future design refinements. Artificial intelligence models analyzed long-term material performance under extreme environmental conditions. High-speed computational systems simulated how microscopic pressure changes evolve over years of operation. Advanced robotics engineers reviewed structural tolerances through augmented engineering environments powered by real-time production data. And all triggered by one small leak. And that is the terrifying precision of modern technology. And because next-generation systems are designed to react aggressively to tiny inefficiencies. Modern electric platforms operate within such optimized performance margins that even minor anomalies become critically valuable sources of intelligence. A microscopic seal variation today could influence millions of future production decisions tomorrow. And the machines understand that. And deep inside automated battery production systems, robotic assembly lines continued operating with astonishing coordination. Massive battery cells moved through thermal calibration chambers, where temperatures were controlled with surgical accuracy. Laser-guided robotics bonded components together while machine vision systems inspected each connection at speeds impossible for human labor. Entire sections of production operated in near silence, except for the rhythmic motion of synchronized automation. And every movement measured, and every component tracked. and every variable monitored continuously. And meanwhile, the vehicle itself kept moving through changing landscapes. Urban centers glowing with reflected neon, desert highways shimmering under intense heat waves, mountain roads twisting through cold atmospheric conditions. The machine adapted, constantly balancing energy distribution, cooling efficiency, and performance optimization in real time. And still the leak remained under observation, and the onboard intelligence never stopped watching. And microprocessors buried beneath the vehicle floor processed streams of live sensor data every fraction of a second. Pressure readings flowed into predictive algorithms trained on billions of operational miles. AI-driven monitoring systems estimated component fatigue progression, while adaptive software recalculated risk models continuously as road conditions changed. And this is where transportation begins resembling artificial life. And not because machines are conscious, but because they react with extraordinary autonomy. They observe themselves. They optimize themselves. They communicate with larger infrastructures continuously. The boundary between vehicle factory cloud network and AI system begins dissolving into one enormous integrated machine ecosystem. And the visual scale of it becomes almost impossible to comprehend. And gigafactories larger than entire city blocks operating at full velocity. Autonomous casting systems producing enormous structural components in minutes. Robotic paint chambers applying coatings with molecular-level consistency. AI logistics platforms coordinating global material movement across ports, warehouses, trains, and cargo fleets with predictive efficiency. And every second of production generates oceans of information. And every vehicle becomes a rolling sensor platform feeding intelligence back into the system. And the leak was no longer just a mechanical issue. It had become data influencing future robotics, future software, future manufacturing tolerances, and future machine learning architectures. Somewhere inside enormous server farms, AI systems were already rewriting optimization models based on what this one journey revealed. And that creates a chilling realization. And the future of mobility is not static. Machines are evolving continuously after deployment. Production never truly ends anymore because software updates, AI learning systems, predictive diagnostics, and manufacturing refinements continue operating long after vehicles leave the factory floor. And which means the real machine is not the vehicle alone. And the real machine is the global intelligence network surrounding it. And an invisible infrastructure of robotics, automation, artificial intelligence, predictive computation, industrial manufacturing, energy systems, and cloud-connected diagnostics, all moving together with relentless speed. Every road becomes part of the experiment. Every mile becomes training data. Every anomaly becomes fuel for larger technological evolution. And somewhere ahead on that endless highway, the vehicle continued accelerating into the darkness, while billions of invisible calculations unfolded behind the scenes. And somewhere ahead on that endless highway, the vehicle continued accelerating into the darkness while billions of invisible calculations unfolded behind the scenes, merging road data, environmental readings, and system intelligence into a continuous stream of adaptive decision-making that never paused, never hesitated, and never lost synchronization, even for a fraction of a second. And the highway itself began to feel less like a physical road and more like a guided corridor of controlled motion. Embedded sensing networks along the infrastructure were quietly feeding updates into centralized mobility systems, detecting traffic density changes far beyond visual range. Heat signatures from distant vehicles were mapped into predictive flow models, allowing routing intelligence to adjust speed, energy usage, and thermal balance before external conditions even became visible. And above, satellite systems tracked atmospheric pressure shifts across entire regions. Below, road-embedded sensors measured vibration frequencies caused by tire interaction with asphalt surfaces aging under continuous load. Every fragment of the environment was transformed into computational input, and the vehicle was no longer simply moving through space, but moving through a constantly updating simulation of reality itself. And inside the core processing architecture, the leaked data remained active as a persistent analytical node. It was no longer an isolated issue but a reference point inside a larger behavioral map of mechanical reliability. Machine learning models began correlating it with thousands of similar micro-events recorded across global fleets, constructing probability layers that expanded and refined with every passing second of driving data. And the deeper the analysis went, the more complex the system became. And robotic manufacturing environments on the other side of the network responded with subtle recalibrations. Assembly sequences adjusted their timing cycles. Material tension systems recalculated force distribution curves. Precision welding robots modified arc intensity profiles based on newly refined durability thresholds. Even conveyor synchronization speeds shifted slightly, optimizing alignment between subassemblies that would not be physically installed until days or weeks later. And everything was connected. And everything was reacting. And nothing in this system operated in isolation anymore. And inside colossal energy management centers, grid balancing algorithms adjusted power distribution dynamically to support increased computational load from diagnostic clusters. Energy flowed like a living current across regions, rerouted instantly based on demand spikes triggered by simulation workloads analyzing the leak's behavior under hypothetical stress conditions. Entire power infrastructures were behaving like responsive organisms, adapting in real time to computational thought processes occurring inside machine intelligence networks. And the vehicle, still moving at high velocity through shifting terrain, became a moving node inside this global machine consciousness. And its sensors captured subtle variations in wind resistance as air density changed across elevation gradients. Adaptive suspension systems recalibrated hundreds of times per second to maintain stability over microscopic surface irregularities invisible to human perception. Thermal systems redistributed cooling pathways, internally redirecting energy flows with precision that mirrored biological circulation systems, except entirely synthetic and exponentially faster. And the leak remained small, but its informational impact was expanding. And in simulation environments, digital replicas of the vehicle began testing extreme scenarios. What would happen if temperature dropped suddenly during high-speed ascent? How would material fatigue progress under continuous vibration resonance? What if pressure loss intersected with rapid altitude change during sustained acceleration? Each scenario branched into hundreds of sub-simulations, each one refining predictive accuracy further. And these were not simple models. And they were evolving computational environments capable of rewriting their own assumptions. And meanwhile, in production ecosystems, robotic inspection units began deploying higher-resolution scanning protocols for next-generation components. Optical systems capable of detecting molecular inconsistencies increased sampling frequency without slowing production flow. Ultrasonic mapping systems penetrated sealed assemblies in real time, identifying structural irregularities during motion rather than after assembly completion. And factories did not stop to investigate problems anymore. And they evolved around them. And the scale of this adaptation was almost incomprehensible. Entire manufacturing zones operated like synchronized neural clusters, each section feeding data into central intelligence layers that redistributed knowledge instantly across global facilities. A microscopic finding in one region could influence robotic calibration on another continent within seconds. And back on the highway, the vehicle passed through a stretch of open terrain where environmental conditions became more extreme. Temperature gradients shifted rapidly. Air resistance fluctuated unpredictably. The system responded, instantly adjusting motor output, curves, battery discharge timing, and cooling distribution networks with near-perfect coordination. And inside the cabin system's silent computational layers continued analyzing every millisecond of motion. And energy efficiency models recalculated optimal torque delivery. Predictive algorithms estimated remaining structural stress margins based on cumulative mileage and environmental exposure. AI-driven maintenance frameworks projected long-term component evolution, as if the vehicle was not a static machine but a continuously updating equation. And still the leak remained a central focus of the system's attention. And not as a failure but as a signal of deeper mechanical truth. And across massive data centers, heat dissipation systems pulsed in rhythmic cycles as processor arrays worked through billions of simultaneous calculations. Liquid cooling channels carried thermal load away from computation cores executing advanced simulation frameworks. Fiber optic networks transmitted sensor data at speeds approaching physical limits, connecting vehicles, factories, satellites, and energy systems into a single unified intelligence layer. And there was no separation between road and factory anymore. And no separation between movement and manufacturing. And no separation between problem and solution. And everything existed inside one continuous loop of perception, analysis, adaptation, and reconfiguration. And even the concept of distance began to lose meaning. A failure detected in motion instantly reshaped production parameters in stationary environments. A refinement in robotic assembly instantly altered predictive models guiding vehicles already in operation. Feedback loops closed across continents in milliseconds, forming an intelligence architecture that behaved less like infrastructure and more like evolving cognition distributed across physical systems. And as the vehicle continued deeper into the night, crossing invisible boundaries between climate zones and digital coverage layers, the leak's influence was no longer confined to diagnostics, and it had become part of the system's learning memory, and a permanent reference embedded into machine intelligence, shaping how future vehicles would be built, how factories would assemble components, and how automated systems would anticipate failure before it could ever manifest in physical reality.